Hi, everybody. This is Vaishak Bell, and this is joint work with Rose Khan. And the topic for today is abnormal predicates about learning categorical defaults from probabilistic rules. The general idea here is that default rules, as we know, is a fundamental concern in knowledge representation. Perhaps the most common example and maybe overused example here is that birds typically fly. And the idea, of course, is that penguins, ostriches, dead birds, or birds without wings, so on and so forth, do not. And so humans are argued to typically reason with defaults until they encounter something that is abnormal, and then they change or retract their conclusion. Here again, the most established use of capturing defaults is via non-monotonic logic or non-monotonic semantics. And the idea here is that you add knowledge and you retract your entailments, and that's the reason it's non-monotonic. You could contrast with this monotonic logics, where as you add more knowledge or more information to the theory, your conclusions don't change. John McCarthy, in fact, proposed a very interesting idea, which is still very popular, the idea of circumscription. And what he suggested is that we control the extension of a so-called abnormality predicate. So there could be many of these. And the idea is that Tweety, who is not abnormal, can fly, as can other birds, unless they're dead, or penguins or ostriches. And that's the idea behind this abnormality predicate. One thing I would like to point out is that there is a wide range of semantical accounts in different logics, different formal systems. But the real challenge, I feel, especially with the rise of machine learning, is how do you learn these defaults? Learning defaults has not been widely studied. Of course, once you have the default, there's a number of logics where you could incorporate these defaults as part of a larger reasoning pipeline, which could include actions or time. But the question of learning on defaults itself has not been studied so aggressively. What we propose in this paper is the idea of using a probabilistic rule learning algorithm called ProbFoil. This is based on ProbLog. And the idea is that we learn an invented predicate. Okay, so this is called the abnormality predicate. There could be many of these. And basically, these abnormality predicates covers all the exceptions to the rule. One could contrast this with classical inductive logic programming, where the hypothesis is supposed to be consistent with all the examples. Here, we don't really require consistency with all examples. So essentially, learned clauses are probabilistic. So maybe this gives you a hint about what exactly this algorithm or the methodology looks like. So the idea is that we first learn a rule such as bird flies, every bird flies. Now this has a probability attached, let's say 0.96, because a couple of examples in your data set don't satisfy this constraint. Okay, so what we do is we add an abnormality predicate here so as to ensure that the probability attached to the rule becomes 1. So for instance, if you say that all birds that are not abnormal fly, then the abnormality extension of this abnormality predicate could capture all of these data points that don't fly. And that goes back to the idea of circumscription, as I motivated earlier. So essentially, this abnormality predicate is capturing every instance for which it's a bird and it doesn't fly. Okay, so now it could happen that these instances that are abnormal could also belong to a class. For instance, it could be that all of these birds that don't fly also happen to be penguins, and then you could add a class such as a rule such as if X is a penguin, then it is abnormal. So you could have many different data points belonging to different classes. But the key idea is that you essentially use one or more abnormality predicates that captures or subsumes a whole number of these classes. And hence you get a rule with the probability of 1. And that's the essence of the idea. So it's a very simple idea. It can work with a number of different learning algorithms, and it's very generic as well. So we evaluate this algorithm using a number of different different dimensions. So we look at quantitative evaluations. I don't report them in this presentation in the interest of time, but mainly the idea is to compare the learning speeds of the algorithm when you compare it to the classical rule learning algorithm of ProbFoil. So how exactly does it affect how quickly it learns, and whether adding an abnormality predicate to capture these exceptions makes learning faster, which would be a reasonable assumption. And in fact, as we show in the paper, it is really true. But to give you an example of a qualitative evaluation we do, you could consider, for example, a more complicated example where there are a number of abnormal birds. So for instance, you could have all birds fly except when they're not penguins or ostriches or dodos. And as expected, three of these classes are essentially collapsed into a single superclass of abnormal bird, and so you basically have the rule that if X is the bird and not abnormal, then you fly. Now, to wrap up, what we argue here is that we have a surprisingly simple approach for constructing abnormality predicates from all negative instances. Essentially, you look for the exceptions and you collapse them into a single superclass. Interestingly, this also enables the creation of nested defaults. So for instance, let's say your data set is such that it's basically studying English birds. And you could say, for instance, English birds are those birds that are not penguins and dodos and ostriches and kiwis. And it could be that in your data set, essentially every bird that happens to be English happens to fly, right? So essentially you don't need to introduce an abnormality predicate with the rule for flying because English captures them. And of course, the English bird itself could be defined using abnormality. So English birds are those birds that are not abnormal. So you could have a nested default where English birds fly, it doesn't mention any abnormality predicate, but the one for English mentions as abnormality. So we show various cases of nested defaults and conflicting defaults, and a couple of these discussions appear in the paper. For the future work, it would be interesting to learn defaults over really large data sets. An example being the never-ending learner data set from CMU. And we also make an argument that we don't necessarily need to restrict ourselves to propfoil. We might consider alternate learning methodologies such as Markov logic networks. And that's something we'd love to consider for the future. Thank you very much for your attention.